Hey there, gang. Um, guess it's time. There's no more putting it off. We're gonna get into 4-4 and 4-5. Um, I hope that 4-1, 4-2, and 4-3, made a lot of sense to you. I hope you were able to kind of grasp at least the major bullet points of those sections. 401 was mostly sort of review of pre-calculus, but hopefully you kind of got like the basics of power series and Taylor polynomials and Taylor series and a little bit about convergence and whether a series converges or not, period. Right? Like sometimes you have a series that, the question that applies would be like, just does this or does this not converge at all? And then sometimes the question is, for what values of x, does it converge? And in other words, what's the interval of convergence? And by the way, this title here, radius of convergence, absolutely sort of refers directly to an interval of convergence. Radius of convergence, you can talk about that in like the same breath. Radius of convergence and get out of there. And interval of convergence. And I guess the last silly little intro thing I want to say is, we're definitely, I guess we're changing gears a little bit, but it's mostly like we're just kind of, I don't know, we're gonna, I mean, as it says right here, we're getting into the tests part one. We're going to like finish really strong. Like we're gonna finish. Stop doing that. Why does? Come on. Anyway, as I was saying, we're going to end Unit 4 by going strong at, does something converge or not, and what might be the interval of convergence. Like we're going to start emphasizing that big time. And even though this is going to be, I don't know, I mean, it might seem a little overwhelming at times and challenging, but I think we'll be okay. I mean, the good news is we've already sort of talked about some of the ways to figure out if something converges or not and what the interval of convergence might be. And what I'm mainly thinking about with that is the whole geometric test, And I'll even like give you a little just to kind of reassure you, look, the geometric series test, and we already kind of know that. Anyway, first show some common Taylor series for some pretty major functions. I'm probably going to attach and give you this handout or this paper. Just kind of understand. And I know I don't want to throw too much at you, but just kind of be aware that this will be like a reference sheet, and that this series x to the n converges for certain x values. This series pretty much represents e to the x, that function, and it actually converges for all values, So there are some major different types, like this one for cosine of x, which converges for every, Anyway, there's like a certain little handful of noteworthy functions and their power series and how they converge or whatever. But anyway, I don't want to spend way too much time on this first part. I mean, the symbol equals can mean many different things in mathematics. 1 plus 1 equals 2, equality of real numbers. This signifies equivalent expressions. It's a true sentence. This is an equation. It can be true or it can be false. You know, like x squared plus 3 equals 7, not necessarily equivalent expressions, but this could be a true statement depending on what, And this is an identity. It is a true sentence, but x must be in the domain of both expressions. Again, this is not the biggest thing we're emphasizing. This example, just to kind of show you one example that could pertain, consider the sentence and how this function basically represents this infinite power series, which happens to be geometric, so we should be able to understand why this power series is pretty much representing that function, because it looks like the common ratio is negative x squared. But for what values of x is this an identity? The function has domain all real numbers, because considering we're squaring x, and that means this entire denominator can never equal 0. So in other words, no matter what we plug in for x, we will never be at risk of dividing by 0. So the function has a domain all real numbers. Each Taylor polynomial has domain all real numbers, but only converges, right, because of the whole geometric stuff. But it only converges when x is in between -1 and 1. So the series has a domain -1 to 1, just kind of like facts or whatever. But let's really get into business. The tests for convergence. We're going to start building a list, like a list that we will have of all the different tests that we can have to see if a series converges or not. So, first we have the nth term test. The good news is we've already seen this in our notes from maybe section 4.2 or something. If the terms don't approach 0, then the series, so if the limit of the terms do not equal 0, then the series has to diverge. So we've already pointed that out, If the terms themselves don't even approach 0 and get closer to being 0, then how can the infinite sum converge to something? But this test is actually inconclusive if the terms approach 0. That's probably not so much good news, right? I mean, if you notice that the terms are approaching 0, then you cannot assume that the series actually converges. Again, just like I talked about in that one mix review. I know that sounds weird, but this test is actually inconclusive. So, I mean, if I give you a series, and you realize that, and you run this test, and you see that the terms are approaching 0, you essentially have to pick another test, because you can't make a conclusion, if that's what you have. So, example, does this series converge or diverge? Well, if we run this nth term test, and we realize that the terms themselves are basically approaching 1/2, then according to this test, this series has to diverge. Okay? So this is one of the first tests you would try. Like when we eventually have our full list of all these crazy tests, they're going to be kind of in like a list of like, which ones you would probably try first because they're the easiest or the quickest or something. This nth term test would probably be near the top of our list as which test we would try, first. Unfortunately, it comes up inconclusive a lot because, just because of that. Now, hey, more, familiar stuff. We also have, our geometric series test. If and only if, right? If the series you are given turns out to be geometric in nature, then take advantage of that and just kind of do a quick geometric series test. So I hope you remember when you can determine that a geometric series converges. We covered it big time, in like section 2 or whatever. So when does a geometric series converge? Well, if your common ratio is in between -1 and 1. So if that's true, then that would be what it adds up to. So does this series converge or diverge? Well, if you happen to look at this and notice that, again, in a vacuum, at the end of the day, when you're given some random, series, there's going to be a lot of different ways. And this is where it's going to maybe get a little overwhelming, but just trust in the fact that we can have like a list at the end of all of this where like you try this, and then you try this, and then you try this. You know what I mean? So if you happen to see that this is geometric, you can realize that your R value is 0.1. Right? Which, boom, right then and there, you know that it converges. Right? So it looks like all this question really wanted was, does it converge or diverge? Well, because of that common ratio that it was geometric, it converges. But, I guess kind of going a little bit above and beyond here, because I don't think the directions asked this, but I guess they could have. You can figure out that it does converge to 1/3. Okay? Now, pause the video here if you need to. Pause the video whenever you want, but pause the video here because I'm going to need you to jump over to section 4.5, like that paperwork. So get the 4.5 notes, handy, or get ready to take some notes that are kind of from the 4.5 handout. And by the way, 4.4 and definitely 4.5, these are lessons that you don't have to, do in one sitting here. Like if we were in class together, we'd be doing, these sections over the course of like 2 days. So if you want to break it up into like a couple of days for 4.4 and a couple of days for 4.5, then go ahead. But I want to show you about this P-series test. This is another really, really basic kind of test. So if you happen to have a series like in this form, 1 over n to some power, we call that a P-series, which is kind of like, you can think of it as power, like a, I don't know, I don't want to get everything all mixed up with like power series, but I got to think that the P basically means, power, but anyway. So if you have a series like pretty much in this form, 1 over n to some power, then it's a very, very, very easy test. The series will converge if P is greater than 1, and the series will diverge if the P, the exponent, is less than or equal to 1. And on that note, if your p-value is exactly 1, which means, the sigma of 1 over n, right? That's a pretty famous series called the harmonic series. And believe it or not, it diverges. Like if you had, let's find the approximate turn. I mean, that'd be like a little experiment, I guess, but no examples. But like 1 over n, so you're talking like 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8. Believe it or not, that diverges. I know, it's one of those crazy... That's why it's such a famous series, you know what I mean? Now, if you had 1 over n squared, right? If your p-value was 2, then it'd be like 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared plus 1 over 6 squared, right? Like that converges to something, or if you had like 1 over n to the -1 power or something, or 1 over the square root of n, that would diverge. But anyway, back to 4.4, all right? So far we have the nth term test, the geometric series test, and the p-series test. So those first 3 tests, I think, are pretty straightforward. You're probably not going to like this next test as much, unfortunately. This is called, and now some new tests. What? That's a good segue. And now the next test. Also, like I said again, you're probably not going to like this test that much. But I don't blame you. But the direct comparison test. Okay? Direct comparison test. So, let A, okay, A sub n be a series with no negative terms. Let's say you had, I'm not even going to, well, I mean, I guess I kind of will as we go about our business here. I'll end up addressing what it says here, but let's say you have some random series, right? Like this. And you're able to compare it to another series because, it's like very comparable. And, well, gosh darn it, I don't want you to look at that just yet. So, let's say you have this series, and you think it's comparable to maybe like this other series, a different series that you can compare it to, and you can figure out easily whether this one converges or diverges, right? So here's how you can run this direct comparison test. If you can be sure, like if you can conclude that your series, okay, excuse me, if you can pretty much conclude that your series is smaller than or equal to, term by term, smaller than or equal to another series that converges. I mean, think about that. If we can show that a series is like smaller than something that we know converges, then we can conclude that our series also converges. Seeing as how term by term, it's smaller than something else that we know converges. Likewise, if we know that our series can be sort of shown to be larger than or equal to another series that we know diverges, then we can conclude that, our series also diverges. So it's actually pretty straightforward um, criteria. Like the actual test makes a lot of sense. You know what I mean? But in execution, it's one of those things where you're just going to be like, how the heck do I know when I'm supposed to run this direct comparison test? How do I know what to compare it to? And I get it, like I know what you mean. I was in your shoes once. And that's kind of why you might not like the direct comparison test that much, because it's almost like it's probably not going to be one of the first tests you try, right? And then again, how do you know what to compare it to? Well, I don't know. We're gonna be doing a bunch of examples, and I guess like practice is gonna make perfect, and experience will kind of help you. I mean, so starting with this one, uh, looking at this, like, is this geometric? No, you can't use a geometric test. The whole nth term test, that's not going to work out because these terms approach zero. And the nth term test is inconclusive with that. And it's not a p-series. It doesn't like fit this mold exactly. So anyway, like I said, like the first handful of tests you would try doesn't apply. You come up empty-handed. So let's try this direct comparison test. And what I'm saying is this is very, very, very comparable to this. You just kind of get rid of that 1 plus. You know what I'm saying? And the reason this is also good to compare to is because this actually is a p-series. And your p-value is 4, which means it converges. Remember, if your p-value, your exponent, your power, is greater than 1, then your p-series converges. So, okay, I'm getting a little excited, okay? I'm getting my second win. So, what do we got to do now? We have to pretty much show that this is like term by term smaller than that, okay? Which, think about it. The only difference between this and this is like there's an extra like +1 in this denominator, which makes this denominator bigger than that denominator. So guess what? If your denominator of a fraction is bigger, that actually means it's smaller. You understand. So there we go. This, because the denominator is bigger, this is actually smaller than this, and this converges, which means so does this, because it's smaller. Okay? Oh boy. It's not going to get any... it's only getting messier here, okay? So just bear with me here, okay? You look at this, and spoiler alert, nth term test will come up empty-handed. It's not geometric, you know what I mean? So here's where I'm gonna just like throw a big curveball at you and go to this handout. And I know I get it. I mean, just have these reference sheets handy, right? But here's what happens here. You can look at this, and I guess starting now, okay, I don't want your head to start spinning, but, when you look at this, have this reference sheet, handy, where you're going like, hey, wait a minute, that looks like... maybe like this, right? And we know that this converges. You know what I mean? So let's all right, so since this converges to e to the x, okay, if we had, x to the x squared to the n, like x to the 2n, then that converges to e to the x squared. You just kind of replace the x with x squared, That's how it can work, you know. And check it out. So we know this converges, right, with just the n factorial. But look at this one, n factorial squared, right? The denominator is bigger than this, and so this is actually smaller than this, so it also converges. I know, just kind of, hopefully, you know, when all these examples are done and we've tried some homework, this one might take a little bit of time to kind of get a handle on, okay? So like this one, we were comparing it to just that, you know, like getting rid of the 1 and, oh, it's a p series. But then for this one, you had to like pretty much go to this crazy reference sheet, you know, to kind of compare it to, okay? Anyway. How about this one? So this is not geometric. You know, the nth term test comes up inconclusive. It's not a p series, right? It's not a p series. Yeah? But maybe we can compare it to, like, check it out. Just saying, like, well, this is kind of comparable to that, you know, which you can even sort of, you can almost like even compare it to just 1 over n to the 1/2, which diverges because it's a p series, you know. So 1 over n to the 1/2, because that power is less than 1, this diverges, okay? And since, you know, what's the difference? Well, since this had a -1 in the denominator, it was making the denominator smaller. And if you make a denominator smaller, then it's going to overall make the fraction bigger. So this is larger than this because it has a smaller denominator. And so since this diverges and this is bigger than that, then this also diverges. All right? So another example here. All right. So, I know I'm throwing a lot of different pitches at you. You know what I mean? But here we go. So 1 over n to the n. Well, this, okay, is actually smaller than like 1 over 2 to the n for n is greater than 2. Okay? Did I say greater? I don't even know what I said. But 1 over n to the n is less than that once you get beyond 2. Okay? And this, okay, what can you tell me about this? I know this is crazy, but if we can show that this converges, if this is smaller than that, okay, how can we really say that this converges? By what other test? How do we know that this converges? Because it's geometric. All right. So therefore our series also converges if it's smaller than that. Okay, as long as, because this denominator would be so much bigger. You know what I mean? If n was 3 or 5 or something. So yeah. So there's like the first round of tests for now, okay? So we had like nth term test, geometric series test, p series test, and then this really sort of open-ended direct comparison test. You know, these other tests are very cut and dry. This test is, I don't know, there's almost like a level of creativity to it, or something, but or like versatility. Now for like a concept. All right, so take a breath, like kind of a definition type concept here. Okay. I mean, once again, if you need to like kind of break up this video, this is going to be a long video. That is definitely not meant to be covered in like one class. So if you need to kind of break this up, then by all means. Or if you got the endurance, then hang in there with me, okay? So here we go. Absolute convergence. Absolute convergence implies okay. If this series converges, you know, like if you take the absolute value of all the terms and make sure that all of the terms are positive. So if that series, you make all these terms positive and it still converges, then the plain old series without the absolute value converges absolutely. Okay? We say that if you take the absolute value and it converges, then we say that that series converges absolutely. Absolute converge. And if this converges, then so does the series in which you would like not do anything. You would not take the absolute value of all the terms, you know. It would also converge. If taking the absolute value of all the terms makes it, you know, and it converges, then leaving it alone, you know, it would also have to converge. Just kind of a fact, just kind of a definition for now. Pause and, you know, write that down, but here we go. Show that this converges for all x. All right? I'm thinking we might be able to compare this to something. I don't think it's not geometric. Okay, so here we go. Taking the absolute value of the sine of x has no negative terms, and this would always be less than or equal to what? I mean, think about the sine of x. What would this have to be less than or equal to? One over n factorial. Okay? I mean, right, think about it. The sine of x is never going to be greater than 1, right? Now, what do you think this converges to? 1 over n factorial, and I'll even give you like kind of a hint. 1 over n factorial. What do you think this is going to converge to? 3, 2, 1. E to the first power. If x is 1, then it's going to converge to 1 to the n all over n factorial. So anyway, the bottom line is it converges. You know what I mean? And since our series is smaller than or equal to that, it is also going to converge. So this converges absolutely. And since it converges absolutely, that just means it converges, period. Okay? Move on when you're ready, you know, pause. And now we're going to get into the ratio test. I think that's going to be it for after we talk about the ratio test, that's going to be it for section 4.4, even though 4.5 is like just the continuation. Now, a little bit of a introduction on the ratio test. The ratio test is going to be one of the big tests you do when the question is sort of phrased like, when does the series converge? You know, not like does it or doesn't it, but like for what interval of convergence, for what radius of convergence, okay? And here's what the ratio test says. Let the series, it's got to be positive terms, okay? And so series with positive terms, and you take the limit of a sub n plus 1 all over a sub n, and you get some limit L, okay? So whatever your series is, you take this limit and you get L. If your limit is less than 1, then the series converges. If your limit is greater than 1, then your series diverges. And if your limit happens to be exactly 1, then this ratio test is inconclusive. So again, you take this ratio, you take the limit of this ratio, okay? And you get some limit, and then you analyze that limit and make a conclusion based on what that is. Okay, so here we go. Let's see this in action. Okay. Now we already kind of know this is going to converge. You know, I think we just saw this. You know that when you compare this to well, it's just it just kind of fits this anyway. Let's do a ratio test, okay? Because to be honest, like a ratio test is probably going to be something you try before you do direct comparison. So here we go. All these terms are positive, so we're allowed to run the ratio test. Okay, so here's what this meant. Okay, this whole like a sub n plus 1 all over a sub n. Whoa, wrong way. So a sub n plus 1, that's this. Okay? Instead of n, you have n plus 1. So this is a sub n plus 1. And this is the original a sub n. So this is a sub n, which goes right there. And this is a sub n plus 1. And so you do this ratio, and you take the limit as n approaches infinity. So what can you do with this crazy thing? Let's actually take this limit, okay? Well, instead of dividing by this fraction, you multiply by its reciprocal, and what's going to end up happening is some canceling, because n plus 1 factorial and n factorial, they're going to cancel with each other a little bit. You know, when you rewrite n plus 1 factorial as this, because it's true, the n factorials can cancel, okay? And what you're left with is just the limit of 1 over n plus 1. And when you let n approach infinity, this approaches 0, which is less than 1, and so therefore it converges. Okay? So ratio test, the algebraic canceling, and then you realize that that limit equals 0, which if you go back to here, your limit was less than 1. That's why I wrote this right here, the fact that it was less than 1. And so this would converge by the ratio test. Let me give you like a little hint or a little piece of advice that you might want to write down off to the side or something. Whenever you see factorials, you should probably at least consider the ratio test. You're going to be working with factorials a lot with the ratio test. So try to start to see some kind of direct relationship between having a factorial going on and using the ratio test. Oh, factorial. So does this converge or diverge? Well, it's not geometric. You can't do the nth term thing. So here we go. Let's do the ratio test, seeing as how all these terms are going to be positive. So here we go. Right there is your a sub n plus 1. And we have to divide by the original a sub n. So instead of dividing by this fraction, I already sort of wrote it as multiplying by the reciprocal, okay? So we know there's going to be some canceling with the factorials. So n plus 1 factorial and n factorial, they just reduce to n plus 1 on the bottom. Okay, so that right there was the result of the factorials sort of canceling with each other. And then this other stuff just kind of got brought down. All right. Well, now what can we do? We have n plus 1 to that power all over just n plus 1. So you can kind of simplify there and do like this power minus the power of 1. And so we can kind of simplify this a little bit more. All right. So now what can we do? Well, we can do that little piece of algebra. And then if we rewrite it again, like actually divide that n, what we're going to have here, and we let n approach infinity, what we're going to have here is, let's see, this would approach 0. So we have like 1 to the infinity power. What do we do? Do you remember from last unit what we do with like 1 to the infinity power? We throw a natural log in there. We bring down the n. And then we realize that this would be infinity. This would approach 0, and the natural log, so this whole bubble approaches 1, and the natural log of 1 is, okay, all right. So now what can we do? Now that we have infinity times 0, can we apply L'Hopital's rule? Nope, not until we rewrite it. So instead of multiplying by n, maybe you remember this little trick, divide by 1 over n. Okay. And now what you would have is 0 over 0. And now you can apply L'Hopital's rule. Good old L'Hopital's. this is gonna cancel very nicely. And so when we actually let n approach infinity, this would just be like a 0. So we get 1. But really, don't forget, people, because of this little trick we did, we take this and put it as an exponent on e. So the limit is e. Now what do we do? Remember, this whole time we were doing the ratio test. So e, we have to kind of go back and think about, is e less than 1, greater than 1, equal to 1? It's greater than 1, and so what our ratio test says is that this diverges. Diverges by ratio test. Okay? This was a doozy. If your head was spinning, the ratio test is not very often going to be this crazy with all this algebra and stuff like that. So just kind of rest assured or rest easy about that. How about this one? Well, let's try the ratio test. That would be the setup. A sub n plus 1 divided by a sub n. Okay. And what's going to happen next is we're going to be looking to simplify. And right here, 3 to the n plus 1 power in right there, and 3 to the n power being right there, that simplifies. Okay? That simplifies. And you're just left with like a 3. Alright? This stuff does not cancel with each other as nicely. I hope you realize that. Okay? Now, once again, something really, really, really clever. Really clever. You do this little trick, and you get to here. Okay. And if you actually let n approach infinity, because if you would have let it approach infinity up here, which maybe you would have done, you end up with like infinity over infinity, and yeah. This little trick is nice. And so letting n approach infinity here, you get 3/5, which is less than 1, and so therefore our series converges. Now, like I said a little while ago, the ratio test is going to be used not just to say if something converges or diverges, period, but if there's like a variable involved and you want to find like the interval of convergence, the radius of convergence. All right, now I want to make sure I'm covering all my bases here. All right, so we had this, so everything's falling into place, everything's all the pieces of the puzzle. So I told you about this absolute convergence stuff. And then it says here in the ratio test that for you to even be allowed to run this test, the terms have to be positive. And so whenever you do a ratio test to find like a radius of convergence or an interval of convergence, you have to take the absolute value first. You have to check for absolute convergence. And that's just because of the criteria, the rules of the ratio test. It needs to be positive terms. Okay? So we throw an absolute value in there just so that we're able to actually be allowed to run the ratio test. Here's a sub n plus 1 divided by a sub n, so we multiply by the reciprocal. And then, hopefully you see that this and this are going to reduce with each other. And even this x to the n plus 1 and x to the n. So there is some canceling, all right? Okay. So, if we let n approach infinity, what do we got? If n approaches infinity, wouldn't this be 1/10? So this is the limit we got. This is like our L. Now, what did the ratio test say? It converges as long as L is less than 1. So what we're going to do next, well, okay, whatever. What we're really going to do next is find out for what x values it would make this all less than 1. So we multiply the 10 over, and remember how absolute value works with stuff like this? Your interval of convergence ends up being, negative 10 is less than x, which is less than 10. That's the whole interval, okay? Now, this was worded specifically as what's the radius of convergence. This is like the entire interval of convergence, right? The radius would be exactly what it sounds like. It would be like half of that. And so from negative 10 to 10, that's 20. That's like the overall range or width of the interval. The radius is half of that. So 10. And so that's basically the relationship between radius of convergence and interval of convergence. That's the relationship. Pretty cool, huh? I know. How about this example? Find the radius of convergence, And once again, the ratio test, when there's factorials involved or x's, the ratio test is going to be one of your big go-tos, okay? So make a note of that. So here we go. Running the ratio test. A sub, up top here is a sub n plus 1, okay? A sub n plus 1, all divided by a sub n. There's going to be some algebraic canceling. Okay? And check this out. Check it out. The limit as n approaches infinity of this. So if you were letting n go to infinity, wouldn't it just make this blow up to infinity? Well, yes it would. Unless x were to equal one specific number. Like if x equals 1, this blows up to infinity. If x equals whatever, negative 5, but if x were to happen to equal 0, then, so it only passes the ratio test and thus converges when x equals 0. It literally only converges for that one x value. Otherwise, this limit is blowing up to infinity. And remember, infinity is definitely bigger than 1. So, yeah. So it only passes the, yeah. And thus converges when x equals 0. So since you only literally have like one value, that means the radius of convergence is 0. Okay? Whew! I know that was a lot. That was probably the longest video I've made to date in my whole career. But hopefully you kind of broke that up in like over the course of a couple sittings. And there's a lot to unpack here when it's all said and done. There was like a lot of different tests, right? Some of the tests were really cut and dry. Some of the tests were like, I mean, I get it. Like this test is like, well, when do I use that, and what do I compare it to? And I get it. There's a lot of uncertainty with the direct comparison test. I get it. But hopefully with a little bit of experience, you'll start to become at least a little comfortable. And I know there was some crazy examples in these notes, okay? But one of the bigger takeaways here is that the ratio test not only can show something that just converges or diverges, period, but the ratio test works great when you're trying to find, for what x values, what interval, what radius of convergence. The ratio test is going to be one of your, biggest weapons, for questions like that. Okay? That's it for now.